In this lecture, we're going to be looking at UV and visible absorption spectrometry. By the end of this lecture, you should be able to explain how UV and visible absorption spectroscopy can be used to determine the concentration of compounds in solution. I want to start by looking at visible absorption spectrometry, or as it's more simply known, colorimetry. And I want to demonstrate it by looking at an example of a potassium permanganate sample. This graph shows where permanganate absorbs light, and we can see that the maximum absorbance is around about 520 to 560 nanometers. If we look at the colour wheel, we'll see that that lies at sort of the yellow end of the green, which means that the complementary colour would be at the violet end of the red, in other words purple. And permanganate has this very distinctive purple colour. So the basic theory is that the higher the concentration of permanganate in the sample, then the more intense will the purple colour be. So this sample here contains 1 mole per litre of permanganate, and it's quite an intense purple colour. The second sample, however, contains a far lower concentration of permanganate. In fact, it's 10 times lower. It's 0.1 mole per litre. And you see the purple colour is less intense because there's less of the permanganate complex in there to absorb the light. So if we then take an unknown sample, so here we've got our 1 mole per litre, here we've got our 0.1 mole per litre, and here's our unknown sample. But the unknown sample has got a more intense colour than the 0.1, but not as intense as the 1 mole per litre. So the concentration of our unknown sample lies somewhere in between 0.1 and 1 moles per litre, perhaps 0.5 moles per litre. That's the basic idea of colorimetry, although an instrument is used to make the measurements far more precise. So this is what a colorimeter is made up of. We've got a source of white light, and that passes through a slit to get a nice narrow beam of light. This beam of white light then is passed through a coloured filter. Now you choose what filter to use, and what you usually do is you put in a filter and it removes all the light that the sample does not absorb. So for the permanganate, we probably want to put in a filter that let through light of about 540 nanometers. Sometimes you don't have a filter of exactly that wavelength, but as long as you choose one near that wavelength, it will work. So only light of the wavelength of 540 nanometers comes through the sample, comes through the filter, and then some of it will be absorbed by our sample, because the permanganate absorbs light at 540 nanometers. The more permanganate in there, the more of that light will absorb. All the light won't be absorbed, so some of it will be detected at the photocell, which can then measure the absorbance. And the higher the concentration, the higher the absorbance will be. So when you're doing colorimetry, what you do is you make up a series of standard solutions of known concentration of permanganate, or whatever you're analysing. You then measure the absorbance for these known concentrations and construct a calibration graph. So here are the points collected from our standard solutions. We then draw a best fit straight line through the samples, and then we measure the absorbance of our unknown sample. So say for example we've got an absorbance of 0.8, then going across to our best fit straight line, we'd find that the concentration was 19. And that's the basic theory of how we can analyse the concentration of an unknown by calorimetry. You will get a chance to do this in experiment 6, where you in fact measure the manganese content of a paper clip by calorimetry. Say we're trying to analyse this sample, this organic sample. Here's the absorption spectrum of it, and you see that it absorbs light with a wavelength of 255 nanometers and of 395 nanometers. Now this is out with the visible region, which of course is from 400 to 700 nanometers. So we could not analyse the sample by calorimetry, but if we had a UV spectrometer, we could analyse it because it's absorbing in the UV region of the electromagnetic spectrum. So although a UV spectrometer is far more expensive than a calorimeter, and we don't have one at school, it works on the exact same principle, only in this case you're absorbing light from out with the visible region within the UV region. But we do find often that organic molecules do absorb light in the UV spectra, so this can be very useful for organic analysis. So by now you should be able to explain how UV and visible absorption spectroscopy can be used to determine the concentration of compounds in a solution.